Okay, today I will talk about deep inelastic scattering. In the discussion of neutrino interactions, we classified things in terms of quasi-elastic, resonance, and deep inelastic. It means, strictly speaking, we should be discussing deep inelastic scattering of neutrinos, of protons and neutrons. But what I will do is the deep inelastic scattering of this is what I will discuss in today's class for two reasons. Number one, the whole formalism of deep inelastic scattering, and also the okay, first it is these experiments that were done first, and it is to interpret the results of these experiments the formalism of deep inelastic scattering is developed, and it is the combination of theory and experiment which led to what we call Parton model. And that is what I will describe today. Obviously, the dominant interaction in this scattering is the electromagnetic interaction rather than weak interaction, because neutrinos have only weak interaction. So if I am going to talk about deep inelastic scattering of neutrinos, it is weak interactions that I will concentrate on. But here we will worry about the electromagnetic interaction. This has two advantages. One, of course, is that weak interactions violate parity, whereas electromagnetic interactions conserve parity. So whatever calculations we are doing, we can impose the parity symmetry on them, and that will constrain the system, so to speak. Second thing, which is also related to symmetry, electromagnetic interaction is based on U1 gauge symmetry. Okay, weak interaction is also based on SU2 gauge symmetry, but SU2 gauge symmetry is a broken symmetry. So taking into account the details of the broken symmetry is a more complicated business, whereas the photon, which is massless in the electromagnetic interaction, which is a consequence of the exact electromagnetic symmetry. So we can impose that exact electromagnetic symmetry also on our calculations, which again simplifies the situation. In fact, you will see that the deep inelastic scattering in the case of electromagnetic interactions, it involves two functions, whereas if you try to do deep inelastic scattering of weak interactions, you need to introduce 5 functions. So to keep the algebra simple, but to understand the full mechanism of what is happening, we will first discuss this process. And as I told you, today's discussion is going to be based on chapter 7.1 of it's written in a somewhat telegraphic language. All the details are there, but they are written in very condensed form, and what I will try to do is to expand on those details a little bit so that the physics really comes out. The physics, you understand the physics details completely, fully. So we have a, let me use exactly same notation that Cheng and Lee do. So you have an electron of energy K interacting with a proton of energy P going into an electron this x is anything, we don't care what the x is. We are looking only at the initial electron. Of course, this is our target, proton is sitting at rest, and we are looking only at the final electron. And the kinematics I have discussed in the last class, and I will also denote the following kinematical variables. Q is k minus k prime, mu is p dot q by n, and w square is p plus q whole square. By the way, this k, p, k prime, they are all 4 vectors, and similarly this q is also 4 vector, but this of course is a number, and in fact if you work out, you see that this is e minus e prime by m, because this p is m000 and q of course is e minus e prime times the corresponding vector. So if you take the dot product and divide by m, you get this.
What is m?
M is the mass of the proton. Now we write down the interaction. So the sort of electromagnetic interaction Hamiltonian we write as 1 over q square times the and also put e square here. do I write this? Yeah, okay, I'll write it. So the electromagnetic current has the form psi bar gamma alpha psi. So, and with a coupling constant E in front. So, the electromagnetic current is E times psi bar E gamma alpha psi. And similarly, we can imagine a proton electromagnetic current psi bar P gamma alpha psi P. And these two currents, they will exchange a photon of 4 momentum q, and so I have the photon propagator 1 over q square. And now this is the effective interaction Hamiltonian. I shouldn't call it interaction Hamiltonian, I should call it the effective matrix element, because now I am taking the matrix element of this effective interaction between the initial states and the final states. And I know that only this electromagnetic current will have non-zero expectation value between the electron fields. So that is why I have split writing it in this form. And the problem here, I know exactly how to write this. Based on the rules of quantum field theory, I can write this in terms of the Dirac spinors. The problem is, how does this field psi bar P, how is it producing this final state X? I have no idea how that is happening. So that is my ignorance, and I don't know how to do the first principles calculation, but what I will do is I assume it is some unknown, but that unknown will satisfy parity symmetry, will satisfy electromagnetic gauge invariance, and all the known symmetries of electromagnetic interactions this unknown will satisfy. Based on that assumption, I will proceed. So, I write it for example as some E alpha, P alpha. This is some vector related to electron, and this is some vector related to proton. Now, I want to calculate mod square, and I sum over all the spins. So, this is sum over all the spins, E alpha, P alpha, E beta, P beta. But I can write it as sum over all electron spins, E alpha, E beta, sum over all hadron spins P alpha P beta. By the way, I shouldn't write it as P alpha because the notation is clashing. Let me use some other symbol here. I will use the symbol N for nucleon. Actually, even here, instead of using the symbol P, let me use the symbol N for nucleon. In fact, what I am discussing will be true both for proton and neutron. Now, next step is to calculate d sigma, and you know the formula which relates d sigma to the square of the matrix element. So there are all the kinematic factors which will enter, and then the mod square, and the kinematic factors will look like this. This is 1 over mod v. I am writing it is the relative velocity between the proton and electron. This can also be written in the form of a Lorentz invariant form, but for simplicity I am writing it like this. And then I have 1 over 2m, 1 over 2e, where e is the initial electron energy, times integral dq k prime by 2 pi cube 2e prime. This is for the final state electron, and then n d cube pn by 2 pi or rather I will so I assume that final state contains the final hadronic state. There are n particles. So for each of those particles I put this kinematic factor, and then this one comes sum over I, sum over spins, mod n square. And of course, what I will now do is separate out what is known, that is the electron part, and what is unknown. And what is known I will write in the form of L alpha beta, which you can think of as sum over electron spins E alpha E beta. And this is okay. Or actually, let me follow exactly what Cheng and Lee have done. So they write d sigma d prime d omega is equal to alpha square by q power 4 times e prime by e times L alpha beta W alpha beta. Where is alpha square coming from? You see that the matrix element has an e square, and e square is 4 pi alpha. So matrix element square has alpha square. So that's where alpha square is coming from. Matrix element has a 1 over q square. So this 1 over q power 4 is coming from there. And this factor explicitly e prime by e we put, because if we are considering elastic scattering, electron proton going to electron proton, at the end of the day you will find that such a factor in the two body scattering. We always have factors like this, final state energy by initial state energy. So that is where this factor is coming from. And everything else, all the rest of it is hidden in this dot product of these two tensors, L alpha beta and W alpha beta. And L alpha beta is related to this E alpha E beta product, sum over the electron spins. And W alpha beta is related to N alpha N beta, sum over electron spins, and all these kinematic factors.
So
yeah,
the matrix element equation, you said E alpha, then you had changed the notation, you didn't complete.
no, oh, sorry, here, yeah, I should write N alpha. Yeah. So the L alpha beta, I know how to compute because I know exactly what E alpha is. So I do that and I find that L alpha beta is equal to K alpha K prime beta plus K prime alpha K beta minus or rather it's written in this way plus q squared by 2 g alpha beta. What I usually have here is g alpha beta times minus k dot k prime times g alpha beta, but I have converted k dot k prime into q square by 2, and in doing so I have neglected the electron mass. Q square is k minus k prime whole square, that is k square plus k prime square minus 2 k dot k prime. K square is me square, K prime is me square. I have neglected them. And minus 2 K dot K prime I have written as Q square by 2. The thing is, I don't know what W alpha beta is. Because I have no idea what the dynamics is. But I know that the dynamics involves purely electromagnetic interactions and okay, plus strong interactions also. And both electromagnetic interactions and strong interactions, they conserve parity. So whatever I write, it should conserve parity. And second, that N alpha is arising due to an electromagnetic current, and any electromagnetic current is conserved. You have J alpha electromagnetic. If I dot it with Q alpha, I should get 0. You remember this? It's quite straightforward. I have psi bar K prime gamma alpha psi K. That is the electromagnetic current. And if I dot it with K alpha minus K prime alpha, I have psi bar K prime K slash psi K minus psi bar K prime slash psi K. K slash acting on psi K gives me ME times psi K. Similarly, this K prime slash acting to the left on psi bar K prime, it again gives me ME times psi bar K prime. So this is 0. So the electromagnetic current necessarily has to be conserved. This is not true in the case of weak currents. And remember, this W alpha beta is coming due to the product of that N alpha N beta. And N alpha is an electromagnetic current which has to be conserved. So if I dot N alpha with Q alpha, I must have 0. Similarly, if I dot it with Q beta, it must be 0. So the symmetries involved in W alpha beta is, it's a symmetric tensor. That's point number 1. Point number 2, it should conserve parity. And point number 3, it should have, if I dot it with Q alpha, I should get 0. Since it is a symmetric tensor, if I impose the constraint dotting with Q alpha, then the Q beta constraint is automatically satisfied. So you try it out as a small exercise. If you write now, what are the kinematical quantities on which this tensor can depend on? Again, let us look at n alpha. The initial momentum of the nucleon, it can depend on what other kinematical quantity that I am measuring can it depend on?
Electron moment.
No, but see, let me draw the, if you want, let me draw the Feynman diagram. That will give you a bit of a hint. So the initial electron is coming like this and going off like this. And I'm drawing a line for the initial proton, but this is a time direction. Actually, spatially it is sitting at rest. And I'll draw 3 lines to actually indicate that it's actually a composite particle. And there is a photon, off-shell photon, Q, which is emitted by the electron, comes and hits the proton. And then proton goes off into these n particle final states. But by writing it in that form, L alpha beta, W alpha beta, what I have done is I have sort of cut this Feynman diagram like this. On one side of the Feynman diagram, there is only the leptons. On the other side of the Feynman diagram, there are only strongly interacting particles. And of course, connecting the two is this photon. So, what are the kinematical variables on which this W alpha beta can depend on? It can depend on P and it can depend on Q. Now, I have given you 2 4 vectors and how many symmetric tensors can you construct out of 2 4 vectors? Three. P alpha P beta, P alpha Q beta, P alpha Q beta plus P beta Q alpha. But there's also 4th one, which is the metric tensor G alpha beta. So, if I know that W alpha beta is a symmetric tensor, in principle there should be 4 terms here. But the conservation of the current reduces those 4 terms to 2. And traditionally these 2 terms are written in the following manner. This my minus the, or rather W1 okay. So imposing the symmetries, we find that these are the imposing the condition that Q alpha times W alpha beta should be 0 reduces the number of the 4 functions to 2 functions, and you find that the 2 functions are, they can be written as W1 and W2, and you see these are symmetric tensors. And also if I dot with Q alpha with Q beta, this will vanish and this also will vanish. So this is a fairly straightforward exercise to sort of test your understanding, manipulation of tensors, and I strongly urge you to carry out this exercise and get this form of W. And note that I have put a normalization 1 over m square here. That is because this is dimensionless, so which means W1 has some dimension, but this has dimension 1. So this product has dimension 2. So I normalized it by m square so that this W2 has same dimension as W1. And if you remember in the discussion of the kinematics of deep inelastic scattering I did in the last class, I said that there are 2 independent variables. One is the energy of the final state electron, one is the scattering angle of the final state electron. So these W1 and W2, they can depend on those 2 final state variables. But instead of writing them as E prime and theta, I have written them as Q square and nu. Mu, if you remember, was E minus E prime by m. So instead of E prime, I am using nu. And Q square, if you remember, is minus 4 E prime sine square theta by 2. So I have exchanged the 2 variables E prime and theta with these 2 Lorentz invariant quantities Q squared and nu. And if you see, the differential cross section is actually I wrote wrote d sigma, but it's actually d square sigma because there are two variables here. E prime and theta, the final state and electron energy, final state electron scattering angle. Of course, in the gamma, it is d cos theta d phi, but it's independent of phi, depends only on theta. Any Feynman diagram, there are external legs and internal legs, and all particles on internal legs have to be of mass shell, because for example, instead of this, let us consider the slightly simpler molar scattering. Electron, 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 electron. This is one of the, after studying Dirac equation and doing the second quantization, this is one of the first exercises we do. So, we write the electron current here, and we write another electron current, and the photon is exchanged between the two. This is external, this is external. So this is on mass shell. This is also, and in fact let me put K1, K3, K2, K4. So I have K1 square equal to ME square, K2 square equal to ME square, K3 square equal to ME square, K4 square equal to ME square. A particle which is visible in the lab, a physical particle by definition has to be on mass shell. So, the initial 2 electrons I see in the lab and the final 2 electrons I see in the lab. So, all those 4 particles have to be on mass shell. But how much momentum is exchanged between the 2 electrons, I don't know. That is a completely random variable. So, I see at this level you can describe this process in different languages. You can, if you want, you can talk of there is a Coulomb force which is pushing the electron. But we choose to use the quantum field theory language because it is applicable in a wider, it can describe a wider range of processes compared to saying there is a Coulomb force pushing from Coulomb force from electron 1 which is pushing electron 2. So if you use the quantum field theory language, we say that the scattering is occurring because the 2 electrons have exchanged a photon, and we insist on conservation of energy momentum at every vertex, which means that K3 is equal to, and I assume Q is flowing this way, then I say that K3 is equal to K1 minus Q. I square both sides. K3 square is equal to K1 square minus 2K1 dot Q plus Q square. But K3 square is ME square, K1 square is ME square. It means Q square is 2Q. Okay, what is Q? Q I will write in terms of, well, I will write this way only. So Q is K1 minus K3. So I substitute that to K1 square minus 2 K1 dot K3. Now this is non-zero, and it has to be non-zero because when I write the matrix element for this process, I have J alpha by Q square, and if Q square is 0 for a on-mass shell photon, for a photon which is visible in the lab, Q square has to be 0. For an on-mass shell photon, Q square is 0, and if Q square is 0, this is going to blow up. So for the whole quantum field theory and this concept of propagator to make sense, an internal particle necessarily has to be of mass shell. And in fact, I urge you to do this exercise so that you will be more convinced. Here I talked about photon, but you do Compton scattering, where there is an initial electron and photon comes and hits it, and it becomes an off-shell electron, and this off-shell electron sometime later, so I have E minus K1, E minus K2, gamma Q1, let me not call it Q, okay, let me call this P1 and P2, I'll call this gamma K2, and this electron has momentum Q, and using very similar arguments, you should argue that Q square cannot be ME square, because using the rules of quantum field theory, if you write the propagator, if you write the matrix element for this Feynman diagram, you have the electron propagator, and you will have in that electron propagator, it will look like this term will come, and if Q square is ME square, this will blow up. So this is a very simple rule in quantum field theory. An internal particle cannot be on mass shell. Otherwise, the formalism doesn't work. I would put it the other way. Formalism of quantum field theory requires all internal particles to be of mass shell.
So this means whenever we have some massive particle in the propagator, there would be a term like Q square minus MW square or something in the
And if the Q square is much smaller than MW square, I neglect it and it appears like a constant, and that is why we have the so-called Fermi constant. Strictly speaking, there is actually some Q square dependence, but that 1 over q square minus mw square. The q square is so much smaller than mw square, so that for 50 years nobody realized the energies are so small that nobody realized the q square dependence. And once the electroweak model was proposed, then one of the important experiments that was done is to explicitly see the q square dependence in a weak scattering process. I was a PhD student at that time. I joined for PhD in 82, and these experiments were first such experiments were done in 79. And while I was a PhD student, of course, they started pushing up the energies. And so there were two accelerators, one at slack and one at DC. So the accelerator at slack was called PEP and the accelerator at DC was called Petra, both E plus E minus colliders. And they managed to push the energies up to about 30 GeV. So then you have a q square of the order of 30 GeV square, which is not negligible compared to 90 GeV square. So you begin to see the effect of the propagator. So anyway, so in this deep inelastic scattering, there are two final state variables, E prime and theta. Instead of E prime and theta, we exchange them with Lorentz invariant quantities q squared and mu. So all the explicit P and Q dependence we have modded out, but still this W1 and W2 can in principle depend on these kinematical variables through those Lorentz invariant combinations. Now, I've talked in some very fancy language about electron proton deep inelastic scattering ... But this is something basic. Any complicated theory that you build should also describe simpler phenomena. Otherwise, the complicated theory is no good. And if you are talking about electron proton scattering, what is the simplest phenomenon you can think of? That is what we discussed in the last class. That is the elastic scattering. And why does the elastic scattering occur? Because electron has electric charge, proton has electric charge. And these two electric charges, they exert Coulomb field on each other. So, whatever procedure we have described, in principle, should also describe the simple Coulomb scattering of electron of proton. In particular, and when we talk about Coulomb scattering, what property of proton are we testing? We are testing its electric charge. strictly speaking, we are also testing its magnetic moment, because if you look at Sakurai and look at the so-called Mott scattering, what I'm talking about, the elastic scattering of electron of proton is Mott scattering. And if you look at the details of Mott scattering, the dominant term, of course, is the Coulomb term, but there is a subdominant term which becomes important when the electron energy becomes higher, which tests the magnetic moment of the proton also. Actually, that is called Rosenbluth scattering. Mott scattering is purely Coulomb interaction, but inclusion of the magnetic moment, that's a little more complicated, and that is called Rosenbluth scattering. So, whatever procedure that I have described, in principle should cover Mott scattering as well as Rosenbluth scattering, which means that these W1, W2 functions, they must have some relation to the electric charge of proton and the magnetic moment of the proton. What's the time? Okay, I'll describe the relation between W1, W2, the electric and magnetic charges of proton, and stop. So, oh, by the way, let me complete the discussion. So, yeah, I wrote d square sigma dE prime d omega in this form, and then I said I don't know what W alpha beta is. But if I write W alpha beta in this form, how does that cross section look? Let me write that formula down. Just a minute. Yeah. Do you recognize the factor that is sitting in front? Where does that come before? Rutherford scatter. And in fact, this is essentially the Rutherford scattering cross section. Of course, that is elastic scattering, so there is no E prime. So in that sense, that E prime is fixed due to the delta function that we discussed yesterday in the last class. So, and what did Rutherford scattering tell us? That there is a point-like particle at the nucleus, and the magnitude is proportional to the square of the charge of that. So, it means that these terms, they have some relation to the proton charge. So we need to understand what that relation is, and also how they are related to the magnetic moment of the proton. To do that, we take a slightly different attitude. What we do is so we take the electromagnetic current for a nucleon and take a matrix element of it, initial nucleon of momentum p and the final nucleon of momentum p prime. And once again, so in principle there are three vectors. This is a Lorentz vector, so right hand side should be a Lorentz vector. The three vectors we have are gamma alpha, p prime alpha. But we have the constraint that right hand side dotted with q alpha should be 0, where q alpha is p minus p prime. So if I impose that constraint, the 3 reduces to 2, and you find that this is u bar n p prime times gamma alpha f1 of q square plus I sigma alpha beta q beta by mn by 2m. Okay. F2 where q is equal to minus p. And if you recollect your Dirac equation, you find this is what we call the electric charge. What is multiplying gamma alpha? That is the electric charge or electric charge form factor, because when q square begins to when you try to measure electric charge, you try to probe the proton with a photon of a very, very low energy, or actually q is not 0, but q square is very close to 0, almost on shell photon. That is how you measure the electric charge. And similarly for measuring the magnetic moment also. But when q square begins to become significantly away from 0, you begin to probe the electric charge distribution and the magnetic momentum distribution of the proton. So this is the electric charge distribution, and F1 plus F2 is the magnetic momentum distribution. But if you remember, this psi bar gamma alpha psi it gives rise to both electric charge as well as a magnetic moment. So electric charge is F1, but magnetic moment is F1 plus F2. And so with this matrix element, if you calculate the Rosenbluth scattering, you have, actually it says d omega here. Alpha square by 4e square. This is a complicated looking expression. First, let me write the denominator. 1 plus power minus 1 sine power minus 4 theta by 2. So instead of that simple 1 over sine power 4 pi, there is this additional factor, and the numerator is even more complicated. Is multiplied by cos square theta by 2 times 1 minus q square by m square power minus 1 times g square minus q square by 4m square gm square minus sine square theta by 2 times q square by m square gm square. So, sorry, g. So if you mod out this 1 over sine power 4 theta by 2 behavior, you have a cos square theta by 2 term, and you have a sine square theta by 2 term, and the sine square theta by 2 term is directly gives you the magnetic form factor, whereas the cos square theta by 2 term gives you a combination of electric form factor and the magnetic form factor. And one can, the relation between G and so we had the W1, we defined the W1 for deep inelastic, but in the elastic limit, there is the delta function which occurs between q square and m nu, and nu, this we discussed in the last class. There is a constraint between q square and nu in the elastic limit. So that is this constraint, and q square by 2m times gm of q square. So W1 is directly related to the magnetic form factor, and the electric form factor W2 in the elastic limit is given by delta q square plus 2m nu times 2m divided by 1 minus q square by 4m square times g of q square minus q square by 4m square gm of q square. So if you remember the deep inelastic scattering cross section, I have written as there is the Rutherford 1 over sine power 4 theta term, theta by 2 term. If you mod it out, there is a cos square theta by 2 times w, rather sine square theta by 2 times w1 and cos square theta by 2 times w2. And the w1 is related to the magnetic form factor, as we see by comparing the deep inelastic term with the Rosenbluth scattering formula. And similarly, W2 gives a linear combination of electric and magnetic form factor. So these W1 and W2 I introduced in the deep inelastic scattering from the point of view of relativistic covariance and the symmetries of electromagnetic interactions. They have a physical basis in terms of properties of proton or neutron, because I'm calling it a nucleon, so it will be valid both for proton and neutron. And in the elastic limit, this W1 and W2 depend only on q square, because q and nu are constrained by this. And in such a limit, W1 is describes the magnetic properties of the proton, whereas W2 is a combination of electric and magnetic properties of the proton. But if the elastic constraint, the constraint that it's an elastic scattering is not there, or in other words, the hadronic final state is a multi-particle state instead of being containing just a nucleon. In general, W1 and W2 should depend both on q squared and nu independently. But experiments showed that W1 and W2 depend on a combination of q square and nu. Okay, if you look at dependence on q square alone, yes, there is some dependence. If you see the dependence on mu alone, yes, there is some dependence. But there is a variable which is minus q square by, I think, 2p dot q or 2m nu. it turned out that it depended, W1 and W2 depended only on this variable but not on the other part. So why should that be? So, but based on our language of elastic scattering, it means that there is some constraint that is coming in. Of course, elastic scattering requires x to be 1. Here, in deep inelastic scattering, x is not 1. It can take any value between 0 and 1. But the scattering cross sections depend only on x. It doesn't depend on. A priori, there can be an arbitrary dependence on q square and arbitrary dependence on mu. But experiment is telling me that dependence is only on this ratio q square by mu, not on anything else. Which means that is giving a hint to me regarding the dynamics by which the nucleon is going into this multiparticle state. And Bjorken came up with some complicated quantum field theory based argument, but later Feynman proposed what we call Parton model, which interpreted this dependence of the scattering cross section purely on x in terms of scattering of electron of a light point-like constituent of proton. So we will discuss details of Parton model in next class. Okay.
So at low energies, this behavior isn't there, right?
Yeah, so it sort of goes in a progress. At the lowest energies, you essentially have Rutherford scattering. That is when an electron is non-relativistic. At slightly higher energies, you have Mott scattering. At higher energies, you have Rosenbluth scattering. So, in Mott scattering, you are okay. This is how the progress goes. At the lowest energies, when you are looking at Rutherford scattering, you are sensitive to electron charge and proton charge and nothing else. You go up to Mott scattering, and there the proton is still a blob. It's the source of a Coulomb field. But you are beginning to sensitive to the relativistic character of electron. So that is when electron energy is hundreds of keV to an MeV. So the relativistic details of the electron you become sensitive when you go to Mott scattering. You go to even higher energies, tens of MeV, 100, maybe lower hundreds of MeV. So you still have elastic scattering, but now you begin to see the structure of the proton. You see the so-called electric form factor and the magnetic form factor. So proton is no longer a point particle for you. And the fact that you have this q square dependence in these factors, that is telling that there is a structure. If the proton, like electron, if the proton is also a point particle, the structure of the elastic scattering cross sections will tell me basically this term will not be there. Or rather, sorry, this term will be there, but there will be a strict relation between GE and GM, which is given by Dirac equation. In Dirac equation, the magnetic moment of electron is proportional to the electric charge of electron. But since the proton has some arbitrary internal structure, that will no longer be true. So, you know that by doing Rosenbluth scattering, you know that proton is not a point particle. There is something happening in there. There is some internal structure. But how that internal structure is interacting with each other, you don't know. But when you go to deep inelastic scattering, where you are breaking up the proton, that is telling you that what are the kinds of things that are actually in there in proton. So that's how the progress goes.
At the low energies, does pions which are there in the nucleus?
I mean, but this language you can adopt to that. But what you will then do is you will see at how the proton is excited to a delta resonance, and then the delta resonance de-excites. So you are not directly probing the pion in the nucleus. See, the pion in the nucleus is again an off-shell particle. It's not really there. The Yukawa potential we use, it arises due to the propagator of the pion. So that pion is off-shell. Yeah.
Unrelated. There is what is this coherent elastic scattering? I mean, there are some experiments dedicated for that.
That is different. See, this is sort of related more to the Hofstadter experiment. So let's take a carbon nucleus. I shoot an electron at it at a very low energies. It will see only the charge of the carbon, nothing else. So it is interacting with the whole of the carbon nucleus. This is the original Rutherford scattering, you can say. But if you increase the energy, you begin to see the internal structure, and you find that the scattering cross section can be interpreted as if it is an incoherent scattering of the electron with the protons in the carbon nucleus. So you take the elastic scattering of electron with a proton multiplied by 6, and the scattering cross section of electron with carbon is 6 times the scattering cross section of electron with proton. So that is incoherent addition. But there is a non-zero probability for the amplitudes to add and square. That is coherent cross section. And since you are adding the amplitudes and squaring, that coherent cross section in principle can be larger. But of course, the probability of that occurring is small. So that is the difference between and some 3-4 years ago, an experiment, I guess at Oak Ridge, I don't remember exact details. There's an experiment which is called coherent experiment, which succeeded in measuring the coherent scattering of neutrinos with a nucleus. How to exactly characterize this coherent scattering? One has to do it using some kinematical details. I don't remember. I have not studied those details, but it shouldn't be very complicated. And what people have been doing in the last 5 years or so is to sort of exploit this new measurement to study some new physics.
Such as?
Well, sort of the so-called non-standard neutrino interactions, and also see if somehow one can whether it will have some advantages in studying neutrino oscillations. People are exploring various different things. I have not tried to follow all those details, but anytime anything new comes up, people will try all kinds of games to see whether this new can be studied to do some other new thing.
Can coherent scattering, can it, so as you said, it can boost the total cross section. So some particular detector material help in having a higher probability of detection?
I don't know. Maybe, I don't know. Off the top of my head, I would say no, but I really don't know.
One more question. This related to this Rosen-Bluth scattering. So that versus this Mott scattering. In terms of Feynman diagrams, would there be more Feynman diagram?
See, Mott scattering you can describe by a Feynman diagram, but Rosen-Bluth scattering, strictly speaking, you can't describe by a Feynman diagram. Because in Rosen-Bluth scattering, you are looking at internal structure of the proton. Feynman diagrams are useful. They are, let me put it this way, they are exact when all the particles involved are elementary particles, or at least can be treated as a point-like particle. If the particle is not a point-like particle, Feynman diagram is an approximation, and what kind of approximation it is, it depends on the situation.